Thank you for the introduction and hosting this great conference. So let me start off my talk with a little story. So you go to a car dealership and you're going to buy a new car. So you talk to the salesperson and you ask him like, hey, if I buy this car, do I get the keys for this car? And the salesperson obviously says, yeah, if you buy the car, you get the keys. So you go ahead, you pay the dealership, you get the car, and you ask, where's my ECU master key? And the salesperson just looks at you very confused. But yeah, this talk is about how to get your SecOC keys for your own car, so you can kind of do with it whatever you want. So I'm Willem Melching, and I also want to give a shout out to Greg Hogan, an old colleague of mine who also worked on this. So the purpose of this talk is to extract signing keys needed to craft messages on the canvas of your own car. In the next 30-45 minutes, we'll learn about car hacking, kind of what approach I take when I take apart an ECU. We'll learn about SecOC, and we'll also learn about this specific exploit on blockchain. So the purpose of this talk, we want to extract the keys specifically needed to sign the lane keep commands or the drive-by-wire, and more importantly, to prove people wrong on the internet. This is a very big hobby of mine. So if people say that something can't be done, then I kind of have to show them that I can. So I'm Willem. I started my own company about 2 years ago after my time at Comma AI. I just do cybersecurity consultancy. I do pen test training, and also some fun research projects. So why this research? Quick introduction on OpenPilots. This is the project I used to work on. It's kind of open source lane keep assist. It's like Tesla Autopilot, but then for your VW Golf. They have a little device that mounts the windshield and performs a man-in-the-middle attack between your lane keeping camera and the rest of the car. And this way you can actually send proper lane keep commands that will drive your car very well. There's many car models supported, over 250. And then at some point for a specific car, a new car showed up. And then usually the community comes in, figures out what the DBC file should look like, ports the car, and then it works. But on this one, there was like a weird checksum that was like 28 bits long. People were struggling to figure out what it was. And then at some point, people realized this was SecOC, or the JASPAR, the Japanese standard. So kind of timeline, these cars started showing up in 2020. And then it actually took quite a while through the component shortages for these cars to actually be built and to get spare parts out there. So in the beginning of 2022, we finally got our hands on a power steering motor. And then we extracted the firmware, and then we had to build an exploit. And like early 2023, we released an exploit. Quick automotive 101. Probably many of you already know this. But it might be interesting to know some of the backgrounds, the limitations of CAN bus, specifically why SecOC is what it is. So the performance is quite low, speeds are low, and classical CAN messages, which this car was using, can only hold 8 bytes of payload. And if you have only 8 bytes of usable payload, you're gonna look into some constraints. And then CAN bus also allows for man-in-the-middle attacks. There's no guarantees on timing whatsoever due to the arbitration process. So it's very easy to just build a device that has a CAN transceiver on both sides, receives a message, modifies it, and then set it on to the rest of the car, and the car will be none the wiser. Typical network topology. There's usually multiple buses on these cars, multiple CAN buses. The OBD2 port will be separated by a gateway. And then the lane keep stuff and the powertrain stuff will be usually separate. And then other cars use automotive Ethernet as well. And then UDS, Unified Diagnostic Services, is used to reflash ECUs in the field. That's kind of the main purpose we'll be looking at. But you can also use it to diagnose problems, read out sensor values, run actuation tests, Because it's a standard, all ECUs speak it, so it's basically the first thing you start looking into when you do car hacking. So we have a request and a response. So a request has a service ID, and then an optional subfunction, and then some payload. And there's very useful standardized error codes that tell you what's wrong. So a useful service that you can do is diagnostic session control, which, for example, goes into extended diagnostics if you want to make some permanent changes to the ECU, or session 2, which is a programming session. And what this usually does, it jumps to the bootloader for reflashing. There's service 23, read memory by address. Usually it's like restricted, where you can only read certain areas, but on this ECU it was actually open for some useful regions that we could use for debugging. So that was nice. Security access. So security access works with a seed and a key, kind of like a token response. So the ECU generates some random data, sends it to you. Then you apply some cryptographic operation. The ECU will apply the same cryptographic operation to it and then compares the results. And if you prove that you know this cryptographic operation, you prove that you know the secret and can log in. In the past, it's just like very bad cryptography, like some XOR or just an addition. And lately, we're seeing more complicated measures, such as like AES encryption of the payload, or like the UDS-29 with like proper certificates. Then we also have routine controls. Think about this as like remote procedure calls on your ECU. So you can start, stop, or get the results for a certain operation. And this is, in this context, used to initiate flashing. For example, you can start a routine to erase a bit of the flash. Then we have request, download, and upload. This is from the ECU's perspective. So download means flashing firmware to the ECU, and we'll be using this as well. So first, if you want to flash an update, you request a download, and then you transfer some data. So more specifically, how do firmware updates work on ECUs? This is a very typical memory layout of an ECU. So we'll have a bootloader, which sits in the beginning of flash. Then we have some application code, which sits after it, and then some data and calibration. Important to note is that I think OEMs want to save as much money as possible. So they want to use the least amount of flash that they can. So they won't opt for like dual banking. I know like only very few car manufacturers do this. So at one time, there will only be one version of the application. So if you want to update it, you have to erase it first and then put a new version in its place. Another thing that's important to know, that ECUs need to boot fast and they're slow. So there's no way that they can do a proper signature check, like compute like a hash of the firmware every boot. So the secure boot is implemented only during flashing. And then when during flashing the firmware is verified, it puts a marker in place that this firmware is checked, and then it will just check the marker every boot. So how does this work? Your application is running normally. You request a programming session, which will redirect execution to the bootloader. Then you run a routine control, erase memory, which then erases your application. So now if you would pull the plug to your ECU, it will just boot up in the bootloader. So now it won't be bricked. And then you flash a new application, which is like request download, and you transfer all the chunks to flash it. And then at the end, you run a routine control again to verify, say, like a hash or a signature. And once that succeeds, it puts the marker back in place so that if you reboot the ECU, it will jump to the application instead of the bootloader. Some quick notes about reverse engineering firmware. This is kind of from my perspective. I basically never seen an AUTOSAR source code in my life. So for me, it's all through the perspective of Ghidra. So we have some automotive microcontrollers. There's 3 common architectures that we see a lot: PowerPC, V850, and Tricore. They're like safety, because of safety requirements, these specify to certain ASIL levels. And because of this, they're usually older technologies. They are less resistant to modern attacks. They're like probably 5 to 10 years behind in silicon design. So most of them are very susceptible to fault injection attacks. So how do we get the firmware off? Well, we can just map out the JTAG pins, and then hopefully they didn't lock it. In the past, a lot of them were unlocked. Now we can see them getting locked more and more often. Yeah, so you try to get it off using JTAG, and then once you have the firmware, you load it up in Ghidra. You run the automatic analysis. You want to disable creating address tables because it always messes up your code. And then you start looking at the entropy. It's very useful to keep the entropy map loaded. And then here you kind of see the same structure as well, where you see like a bootloader sitting here, and then you see some application code. Then I usually start looking for diagnostic handlers. I first start with like XCP and CCP, because if that's enabled, there's like debugging protocols that give me full memory access. So I can look up for error codes. And if I find that, I might find the XCP handlers. Same for identifying UDS handlers. They can usually be found very quickly by looking for error codes such as hex 36, which is like too many attempts, which interestingly is probably only used in a few places. And you find this security access function real quick, where it's like you see some comparison with a counter, and if you have the key wrong, it's error code 35, and if you go over some certain number of attempts, you get error code 36. And from this point, you've identified like the security access handler, and you can work your way back up there to the other diagnostic handlers. And with this, maybe within an hour of getting a firmware, you can find like all the diagnostic handlers. If that doesn't result in anything, or you want to find some more information, you can find the data sheet, look at the CAN registers, and then start seeing all the references to that, and then keep tracking that down. Also very useful in understanding the firmware is that these firmwares use a lot of global variables for some reason, which are like easily, you can map them out in RAM, you can see all the references to them. And if you have like a debugger or some way to read memory, you can also read their state, which is useful in understanding how a firmware works. You see there's like these large structs. I think it's like a result of all the code generation that is going on. But yeah, once you start mapping out these structs, you can make the code way more readable. Some patterns you also see, like for CAN parsing, it's either table-based. So they have like a function that parses out a certain CAN message, and they look up a table like signal ID this and this, which says, oh, it starts on this bit, it's this many bits long. It's kind of like a DBC, but then encoded into your firmware. Something that's also common is like just explicit parsing codes with like shifts and ands and or. I really hope for the people who wrote this firmware that this was auto-generated and not handwritten. A good way to find these is in Ghidra. You can just ask it to export all the code that it knows about to C or C++, and you write some regexes to find like the combination of shifts and ands that you know builds a certain CAN packet, and this will lead you to the handlers. Quick note about AutoSAR. It's basically this whole load of standards that are used to build this automotive firmware. I mean, probably the people sitting in this room know a lot more about it than me. But what we can use it for is that there's like certain standards for certain signatures. So if you very once in a while you will notice the some public API that's used, so you can like find the real arguments. And there's also a nice script from the Renault research group that basically, with calls to the that report error function, can figure out like what the name of like a whole bunch of functions are should be, which is very useful. That's a quick introduction on reversing automotive firmware. Then we'll get to SecOC. So I'll go a little bit slower on this for people who are not super familiar with SecOC intricacies. So in the past, we had checksums, which were usually 2, 4, 8 bits on CAN messages. I mean, CAN already has a CRC, so technically, I think we don't need this. But for like extra safety stuff for like SIL or ASL, We want to make sure that there's no like bit flips during memcopy operations or other weird stuff where we copy like half a message or something. So we want to make sure that like every time we check a message in memory, we want to make sure it's like integrity is correct. So we see very basic checksums like the sum of all bytes or some XOR or maybe a CRC8, and these are all very fast to compute, but they're not real. They're not going to stop me from like forging a message basically. And if they do, it's like some algorithm that once you get the firmware, you just look at the algorithm. So kind of security by obscurity. So this changed with SecOC. So it's an AutoSAR standard. It's authentication. So we know a certain message is sent by a certain ECU. It's integrity protection. So we know that the message is still the same, that nobody tampered with it to put like a different lane keep command in it. There's rollback protection. So you can't just like gather a database of valid messages and then replay them later whenever you need them. This is done with the freshness value. The overhead still needs to be very low. We're dealing with like not very powerful microcontrollers, and this needs to be real time still. So it needs to have low processing overhead, but also space overhead. Say we have a message that can only be 8 bytes long. So if we want to stick like an HMAC in there or like some RSA signature, well, that won't even fit, let alone that we have space left for the payload. So we need a message authentication code that we can just take as many bits from as we need for like our level of brute force protection. And the AES CMAC has these nice properties where it's very fast to compute because it's AES. And we can also just take as many bits as we want to get like a certain level of security. So how this kind of works is that we have a secret key on both sides. It's a symmetric key, so both ECUs have the same key. Then we have a payload that we want to encrypt, or well, sorry, not encrypt, that we want to sign. And then together with the freshness value, we can create a MAC. And then we build the CAN message by basically putting the payloads, because we need to send that. We put part of the freshness value in there and part of the MAC. And then once that message got received on the other side, we can do the same computation based on the few bits of the freshness value in the message. We reconstruct the whole freshness value, we recompute the whole MAC, and then we check if the bits that we do have from the MAC, that they match. So what is this freshness value? It contains of a trip counter, which should go up every ignition cycle, or like when the ECU reboots. And this is the actual rollback protection. And this should also be stored somewhere in like non-volatile storage, that if you get the next power cycle, that this value can only go up. Then there's a message counter. Every time an ECU sends a message on a certain arbitration ID, this counter goes up by 1. And then to keep everything in sync, there's like some node like the gateway that will send like a periodic message that will reset all the message counters for all the ECUs in the car. So everyone like starts with a clean slate, and then when the gateway does this, the reset counter goes up by 1. And then basically we construct this freshness value, so we concatenate the trip counter, the reset counter, the message counter, and we take the last 2 bits of the reset counter. We call this the reset flag, and we stick it at the end again. And this means if we take like say the last 4 bits of this freshness value, we should be able to reconstruct the whole thing if we didn't miss too many of them. And of course, like these actual bit numbers can vary a bit, and it's like probably part of the XML files, or you read it from the source code. And this is like what Niels was talking about. Every OEM does this differently. So then we construct the data to the authenticator, which is usually a message ID, the payload, and then the freshness value. But this can also include padding or other things. Then we compute a CMAC on it, and then we take like the upper bits of this MAC and stick it in the message. So this is basically the message. So then we get to key management. So we need this symmetric AES key. So we need these secret 16 bytes, and both ECUs, like the sending part and the receiving part, need to have the same key. And we also have some other constraints, like say a part is replaced by the workshop. We need to be able to put new keys in them without like sending the keys in plain text. So this is part of the SHE, or Secure Hardware Extension standard. And there's like a bunch of keys defined. And one of them is the master ECU key. And this is relevant in the key update procedure. So basically this is what the key update procedure looks like. So in the workshop software, you put in a new ECU, and then the whole car needs to be provisioned with new keys. So you send up the serial numbers of all your ECUs to the manufacturer's API. They look up this serial number in some database or some key derivation function, and it basically figures out what the ECU master key for that specific ECU is. It generates a new key and a counter for like rollback protection, and then runs it through like a generator. And basically what it does, it generates a bunch of values which contain the new key, but then encrypted with this ECU master key. And this can also be the previous key, but it's encrypted with a key that an observer on the canvas won't know. And most interesting is M2, which contains some flags on like the permissions of this key, and then the actual new key. So in this case, when we're doing our research, we were actually able to capture an XML file just straight from disk, which contains these values. We saw the same values on the canvas, but they're absolutely useless to us. So basically, we were at a dead end now. We could observe everything we wanted, but we could not figure out what the SecOC keys were. So it was time for firmware extraction. So now we'll get into the more practical part of it. So we started with this first car kind of that showed up with SecOC from this brand, and then later more showed up, but we just kept focusing on this one. So we looked for an ECU that we thought was the easiest to target. So we want something with like hopefully not too many security features, something that was easy to extract the firmware for. So we decided to target the power steering because of this, and also because of our experience with this. But they mostly have SLD microcontrollers that are easier targets. So unfortunately, we had to buy a whole rack because there was no cars on Scrapyard showing up. So we just bought the whole new rack. It was over $1,000. And then we took it apart. And then inside it, we found this RH850 with JTAG locked, unfortunately. In the past, we always had seen that JTAG was not locked. So we just dump it. So I started looking into some attacks. Actually, it's very interesting because you connect, there's like a flash utility, and you connect it just a regular UART, just 2-wire. And it like asks you set up the baud rate, and then it connects, and then you get an error code, which says like serial program and connection is prohibited after like a bunch of back and forth communication. So JTAG is, or like debug is definitely not off. We can still talk to it and like configure baud rates. So apparently there's this whole flowchart that it goes through where you set up a bunch of stuff, and then once you've done all the setup, you run like a synchronize command, and then it will tell you, oh no, sorry, I'm actually locked. So now it's time for some volt injection. This chip has 2 cores, so it has 2 regulators inside that generate like a 1.25 volts core voltage, and they're conveniently brought out to capacitors for filtering. So this is a very good point to do some voltage glitching, and luckily it was not a BGA part or anything, so we just see where this was going. Took off the bypass capacitors, put on two NFETs to do crowbar glitching, so we basically brown out the chip very shortly, which causes all kinds of issues. Yeah, and then it's kind of what it looks like on a scope. And I actually did this with a Raspberry Pi Pico, so I chipped this glitch this chip with like less than $10 in hardware. If we don't count that Sele in the back, which is a lot more expensive than $10. And I was going to set up something proper, but just a while loop for a delay was good enough here if you have some patience. So you just need a Raspberry Pi Pico and some Python script. And if you glitch in the right time, just after this synchronize command, sometimes it will give you an OK. And then sometimes the chip is not messed up after this, so you can actually read the whole flash. So you only do this once, and then the whole flash starts coming out. So now we had the firmware. So now was reverse engineering time. We spent a lot of time on this. We did a lot of kind of like standard pen test stuff that probably a lot of you go through as well. So the first thing we looked at, just without the source code, is like, can we bypass this validation? Like, is this SecOC validation like actually done in this ECU? Because the signal is going through the gateway first. So first thought was, okay, maybe it's just the gateway that's verifying all the SecOC stuff. This was not the case. Then we did another just general audit. We looked for XCP, CCP, nothing there. UDS read memory was there, but it only allowed us to read a very small portion of RAM. So it's interesting because it contains some like counters on like which messages were being parsed, but it wouldn't give us anything useful. Also SecOC itself, no issues there. There was something very interesting we noticed though. Even though this chip has an HSM, they weren't using it. So all the crypto was done in software, which just means that the key is somewhere sitting in RAM. So that was very useful, but now we just need to get it out. So this is something to keep in mind. And then, of course, we had JTAG, so we noticed that the key was actually, like this key was coming from like non-volatile storage somewhere, some like EEPROM emulation layer. And then we basically had one ECU, so we could check at this ECU master key. And then we looked at like the key updates, and we hoped that multiple ECUs would reuse the same ECU master key, but it also was not the case. So they were probably provisioning each ECU with a different key. We could, of course, try to change the signing key. With JTAG, this is possible, but this is like a very invasive solution and not something that an average user can do. We did find some interesting routine controls as well as special arbitration IDs where we could like temporarily load new keys, but they were all using the same verification logic with like the M2 and the M3. So without knowing the ECU master key, there's no way to get this. We also looked for like a setting, maybe like a coding or like some routine control to disable SecOC. Also didn't find it. We did notice there was like a 1 second timeout on boot where it skips SecOC validation, probably for everything in the car to boot and wait for the first synchronization message. But yeah, 1 sec. We could like reboot the power steering every second, but this didn't sound like a great solution either. So yeah, we had some other interesting findings as well. So I mentioned in the beginning that the trip counter is for anti-rollback, but this issue just accepted any trip counter on boot. So I didn't store it in non-volatile storage to check if it was actually going up. Two non-standards UDS functions, AB and BA, which parse some like weird ASCII commands. Tried to figure out what they did, but it wasn't very useful, it seemed like. And also very interesting, so each ECU from the factory had a provisioned master key, but the SecOC key was actually a default value. So if you really wanted to know the keys to this specific ECU, just buy a new rack for $1,000 and you know the key, but look for a better solution. Then I started looking into the bootloader and the reflashing process. And then we noticed that the request download allows you to request download into an area of flash and also an area of RAM. And then we noticed that there was no code in this bootloader that actually handles touching the flash. Normally when a bootloader is rewriting part of the flash, what it does, there's like certain routines that it loads into RAM, because you need to be running from RAM when you start messing around with flash. It relocates some stuff into RAM, and then that code handles the actual rewriting of the flash. But we noticed that this issue didn't have any of this code, and there was a request download into RAM that you could do. So our assumption was kind of that before you can start flashing this ECU, it expects you to upload not the second stage bootloader, but just like very specific flashing routines into RAM that would then handle the actual flashing once you start requesting downloads into flash. This means we can upload some code into RAM and then ask the ECU to execute it. But yeah, this turned out to be a lot harder than you might think. It's just a lot of like obscurity here. we couldn't just put some shellcode there. This like ECU was expecting some like a certain type of payload with like some like header at the end with like a COC and like also another CMAC, and this whole thing needed to be encrypted as well. But luckily this was all, I mean, security by obscurity at this point, because we had the whole firmware. They were using AES key that were also in this firmware that we extracted. So it was just a matter of like going through all the steps to build this payload, build the authenticator, and then encrypting it. And they were like, before you could do this, you had through some like write data by IDs, you had to set up an IV and some like other key that is then used to derive the key. I mean, I won't bore you with the whole details, but there's like a lot of steps involved to get this payload decrypted in the right place. And then we actually needed to build a payload. So luckily the V850 compiler is just part of upstream GCC. Just have to build it yourself. So I built a quick compiler for it that could compile the payloads. Wrote a little bit of shellcode in C that just starts dumping out a part of the RAM. Remember when I said that the keys were in RAM? So by this point, we figured out where this area in RAM actually was. We also noticed that when you jump into the bootloader, it doesn't clear RAM. So the RAM from the application was still in place. So this was the easiest way to dump it. We could have just as well got it from the EEPROM as well. And then basically it sends out the contents of this RAM area over CAN. So we, and then at the end, we basically call into whatever function ECU UDS ECU reset calls. So after our payload is done, we just reset the ECU cleanly. And then I wrote some Python to kind of like encrypt this payload, put the MAC in the right place, compute the CRCs. And then, yeah, we kind of had a working payload that we had code execution, and we were able to extract the keys over CAN, so we had a CAN-only attack. And this would work on any ECUs, because all the keys were in the bootloader for updating the firmware were static. So yeah, quick summary. So we want to exploit an ECU. We use routine control, we use service 10 to go to the bootloader. This works as long as the engine is now running. Then we authenticate using security access. We get a seed, do some magic AES on it, give it back the key. Then we do some write data by identifiers to write the AES key and the IV for the key derivation used for the payload. Then we upload the encrypted payload to RAM. And then what we do is we ask the ECU to erase a little bit of the flash, which will then trigger the execution of the flashing routine or the payload that we just put in place. So this won't actually erase anything. This will just trigger the payload. And this dumps out all the keys over CAN and then resets the ECU. Yeah, so I have a quick demo. Let's see. Yeah, so the power cable is a bit short, but the ECU is here. And we can see this is just printing all the CAN messages that come in, so we can see that it's alive. Stop this. And then we run extract keys. It goes very quickly. Boom, done. So basically this walks through all the steps. It does like security, checks the firmware version to make sure we're dealing with the bootloader we're expecting. It goes through security access, sets up the IV and the key and just all zeros. It uploads the payloads. It verifies the payload, so important that checks the MAC. And then we trigger it by asking for a erase, and then we get our ECU master key. In this case, this ECU has never been in a car, so it's not provisioned. So the key will be just all ones. Yeah, so in conclusion, we basically found two vulnerabilities. One was code execution in the bootloader, which is basically present on all the new models that we found for this particular power steering. It's very interested, so this is not fixed. And then we also found that the SecOC keys were just stored in plain text in RAM or in non-volatile in like the EEPROM emulation. And this was only found on 2 models. So the OEM or the tier 1 realized this at some point, maybe even before our research, and already fixed it. But the code execution is still there, which is interesting. Also just want to give credit to the people who built this. We probably spent many evenings, probably over 250 hours in pen testing this thing. We found no real issues in the code itself, like no memory corruption issues. It was just like kind of a bad specification of how the update procedure worked, which just took a lot of reverse engineering to figure this out. There's an exploit POC on GitHub, so you can see how the payload is built exactly. So yeah, the HSM is now used, so there's no more plain text keys. But I haven't spent much time on reversing the specific HSM yet. Maybe there's like other vulnerabilities. And worst case, we could always, just since we have code execution, we can always patch out any of the checking of the SecOC. So then we don't get the keys, but then we can still send messages to the specific ECU. Or if we're looking at what a more hostile person could do, is they could just talk to the HSM. So they can just ask the HSM to sign messages for you. And kind of turn this ECU into a signing oracle for and send messages to other stuff in the car as well. That's kind of why I have some recommendations. So if you're in pen testing, or if you're an OEM and you want to make sure that this doesn't happen to you, these are kind of the recommendations I have. So make sure your HSM in the chip is actually used. I think with all the abstractions that AUTOSAR gives you for all the crypto abstractions, it can be kind of hard to tell if the HSM is actually used, because they also have a bunch of software implementations. So I don't know, like look for the AES S boxes in your firmware, and if you see any, maybe figure out why, and hope they're not actually used for SecOC. Also something that would have made my research very difficult if they had removed the keys when entering the bootloader. You might still find a way, but it would just have made the research a lot more annoying. Also use different SecOC keys for different message IDs. So don't use the same one for the whole car. And you can actually set like permissions to use a certain ECU can only use this key in the HSM for verification and not for generation. So if you do get code execution on this ECU, you can't just turn this HSM into a signing oracle for the rest of the car. And this is an important detail, but then of course you need an HSM capable with enough key slots to actually do this. Also implement proper secure boot and use RSA on your update files. Also a quick note on responsible disclosure. This kind of research I do in my free time. So in the end, I want to be able to talk about it. And if you have like disclosure policies that prevent me from disclosing anything until there's a resolution, which I think in many cases there won't be, well then I can't disclose, which would be a shame. So I'm happy to work with manufacturers. I can give plenty of time to try to come to a resolution, but if there's no resolution, in the end I still want to publish. And I think that's important for consumers to know as well. Questions?
So